Hi again, everybody. That looks like everybody's back. So let me make a start on this session. Now we're going to look at some actual syntax for OpenMP parallel regions and how they work. So the parallel region directive, so remember that the code within a parallel region is going to be executed by all threads. So syntax looks like this. So for Fortran, $OMP parallel, and then a block of code, and then OMP end parallel closes the parallel region. For C or C++, send hash pragma OMP parallel, and then a block of code in curly braces. A couple of things to note for C and C++ programmers. So actually what follows the parallel directive, strictly speaking, is a C or C++ structured block. So that can, in fact, be a single statement without curly braces. However, I'd discourage you from doing that because it's then a little bit unclear as to where the parallel region ends. And it's then easy to make a mistake by deciding you have a one-line parallel region, you then decide that you want another line of code, and then you forget to add the pair of curly braces. And you end up with unexpected behavior because the line of code that you added that you thought was inside the parallel region actually isn't. So I would encourage you, even if the block of code is only a single line, still to use the pair of curly braces to make it absolutely clear to yourself and anybody else who's reading the code what the extent of the parallel region is. The other thing that's slightly unfortunate is that you cannot put the opening curly brace on the end of the parallel directive. The reason for that is that the code has to parse correctly as C code without the directive. So unfortunately, you cannot use the style that you're probably all used to for loops or if statements is to put the opening curly brace at the end of on the end of the line. Okay. So just to remind ourselves what happens here. Okay. So suppose I have here I have a parallel region and it just contains a function call, one function call to Billy here. So what's going to happen in this case is, just to recap, the master thread will execute Fred. So it then logically creates a team of threads to execute the parallel region. All the threads execute function Billy. At the end of the parallel region, the master thread waits for all the other threads to finish executing Billy to reach the end of the parallel region. And then the master thread can carry on and execute Daisy. We'll find that a lot of the time we don't end up just programming with bare parallel regions. We tend to use these work sharing directives to parallelize loops. But nevertheless, if we just want to use parallel regions, then to do useful things, we need to identify or find out typically how many threads are being used inside the parallel region, how many threads there are, and which thread is currently executing, which thread of I. This is done with library functions, runtime library functions. So in Fortran, it's OMP underscore get num threads. Okay, returns an integer. Same in C or C++. So this is a good point to introduce how to use the library functions in Fortran. So these are defined by the specification. These are not compiler dependent. You can do to get the function prototypes. You can do use OMP lib. So that's a predefined module which contains all the prototypes for the OpenMP library functions. And in C or C++, it's a predefined header file. It's called omp.h, so you can just include that. Okay, so if we call this function inside parallel region, it tells you the number of threads in the team that's executing that parallel region. You can call this function outside of a parallel region, but it will, if you call this on the master thread in the sequential part of the program, it will return the value 1. Okay, so this function tells you essentially the meaning of this function is how many threads are there currently executing. It is not how many threads will be used for the next parallel region. There is a way to get that value, but it's not this function. And then to get the number of the executing thread, so this is OMP get thread num. Okay, so it wasn't the greatest choices of function names. They're a bit too similar. So just make sure you don't get mixed up between OMP get num threads and OMP get thread num. So this function takes values starting from 0, which is the master thread, okay, and 1 less than whatever OMP get num threads will return. So thread numbers start from 0. Fortran programmers beware. Okay, so if you're used to array indices starting at 1, this can trip you up. So that's the absolute bare basic syntax for parallel regions. We can then specify some additional information in the parallel directive through what OpenMP calls clauses. So this is extra syntax that goes on the end of the parallel directive. So we can have multiple clauses, and you can either separate those with commas or spaces, whichever you prefer. And in particular, use of clauses is to specify the behavior of variables as whether they are shared or private. So basically, again, remember, inside a parallel region, variables can either be shared, all threads see the same copy, or private, each tell its own copy. So to control this, we have shared, private, and default clauses. So syntax is pretty similar for both languages. We have shared clause takes a comma-separated list of variables in braces, normal braces. Same for private. And then we can also specify the default behavior. So this will apply to all variables which are not explicitly listed in one of the other clauses. So in Fortran, we can set the default to be either shared or private or none. In C and C++, we don't have the default. obscure technical reasons, which I won't go into, you can only do default behavior can only be shared or none. However, that's not a big deal for reasons which I will come to. Okay. Some important things to note about using shared and private clauses. On entry to a parallel region, private variables are uninitialized by default. Okay? So if we declare a variable as being private, every thread gets a new copy of that variable, and those copies are uninitialized. And so it's up to us to make sure that we don't use uninitialized values. If we declare variables inside the scope of a parallel region, those are automatically private. Okay, so that's another way for C and C++ programmers, another way and usually a more convenient and sensible way to create private variables is simply to declare them inside the scope of the parallel region. When the parallel region ends, those private copies disappear. They go out of scope. But the original variable that had that name is unaffected by any changes that we made to those private copies. Okay. So the original variable is not accessible from inside the parallel region, but we are guaranteed that once we exit the parallel region, it hasn't changed from what it was when we entered. Okay. This all works for C++ objects. Okay. In C++, if we declare an object as private, these are created using the default constructor. So it will invoke the default constructor to create the private copies. The next bit I'm going to emphasize as extremely important because this was probably the single worst design decision that was made right at the very start of the OpenMP specification. If you don't specify a default clause, the behavior is the same as if you specify default shared. So without any default clause, variables are shared by default, which is very dangerous and is a very likely source of unintended race conditions. So as a piece of advice for coding OpenMP, I would strongly encourage you, despite the extra typing that it involves, always use default none. Okay? And force yourself to declare all variables, think about the behavior of all the variables that are referenced inside the parallel region and make an explicit decision and an explicit statement in the code as to whether they are shared or private. Otherwise, it's just all too easy to miss something that should be private for correctness. It gets shared by default, and you introduce a race condition type bug, and you get strange, weird, non-deterministic behavior of your program. So there we go. Always, 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 always use default none. Okay. That should have been the default behavior anyway, but it wasn't. And I think that was, personally, I think that was a big mistake in the design of the original design of OpenMP. So consider yourselves suitably warned. Okay, so constructing meaningful code with just what we've learned so far is a little bit difficult. So this is something of a contrived example. But suppose I want, suppose I have some shared array, which has 4 columns in it, and I want each thread to initialize part of the shared array. So Andrew said, yes, it's very reminiscent of implicit none in Fortran 77. So yeah. If you're old enough to remember Fortran 77 and it's exactly the same deal. Okay, so Fortran 77 had this terrible feature by which the type of a variable was implicitly determined by the first character of the variable. Okay, so and you could put implicit none in your code to yeah, absolutely. So still a lot of it, still a lot of Fortran 77 still hanging around. Absolutely, yeah. So you could put implicit none to force every variable to be explicit, the type of every variable to be explicitly declared. This is exactly the same deal. Okay, so relying on default behavior is dangerous and liable to cause nasty bugs. Yeah, in a very similar way. Yeah. Okay. Yeah. Okay. So a shared array, we want to. So suppose we want every thread to initialize a different part of it. So for simplicity here, I've got an array with 4 columns, and I'm going to assume that I'm going to use 4 threads. Okay, so slightly glossing over how we arrange for the fact that there are 4 threads, but we've seen how we can use the environment variable to do that. And so each thread to initialize a different column of this array. So what I can do is I create a parallel region with a #pragma OMP parallel directive. Okay, and then let's look at the code first. So I want to read the thread ID. Okay, so I call OMP get thread num, store that in a variable my ID, and then use that to index the column of the array and set those values to the value 1. Okay, so take my own advice. I will specify default none, force myself to declare everything. So all the variables that are used inside the parallel region. So in particular here, so we have my ID. That needs to be private because I want every thread to have its own copy and store a different value of the thread ID. I also need I to be private. I need every thread to have a separate loop iterator. But the array can be shared, and that's okay because although I've got multiple threads writing to the array, they're writing to different elements of it. So that's safe. And the other variable I have here is the upper bound for the loop, n. Okay, so that's not modified inside this piece of code, so that's fine for that to be shared as well. Okay, that's kind of weird looking coding style, and in fact, in practice, it would be much more natural to use the C language scoping rules to deal with our private variables here. So it'd be very natural to, and actually better coding style would be to declare declare my ID and I inside the parallel region, and that automatically makes those private. And in fact, I cannot also declare them as private on the parallel region directive because they're not in scope at that point. Okay, so anything that appears in the shared or private clauses on the parallel region must have been declared previously and must be currently in scope for it to make sense. So this would very much be the natural way of coding this in C. In Fortran, we don't have such luxury, and so we have to take care of the private variables. Okay. In this way, so we have to declare them explicitly, but otherwise everything's the same. In fact, for Fortran, loop iterators are actually special things. Okay, so in C, loop iterators are just normal variables. In Fortran, loop iterators have a special status, and in fact, loop iterators are always made private by default. So I don't actually, strictly speaking, I do not need to include I in the private clause here. Because it's a loop iterator, it will actually be privatized by default. But otherwise, everything's the same. Okay. Bit of syntactic trivia. Okay, so if we're going to force ourselves to use default none and list all our variables, then it's possible that our directives get quite long. So we need to know how to break those over multiple lines. In Fortran, that depends on whether you're in fixed source or free source form. So in fixed source form, then the new line has exclamation mark $OMP ampersand at the start of the continuation line. In free source, the ampersand goes on the end of the line, and then the next line doesn't have the ampersand. In C, C++, or C++, it's just the usual way of carrying on preprocessor directives, a backslash at the end of the line, and then just carry on with the rest of the directive on the following line. The gotcha to be aware of here is that the backslash has to be the last character on the line. So if you have any trailing white space after the backslash, then this will probably cause a compiler error. It will then try to interpret the continuation as a C statement, and you'll probably get some nasty, weird errors or cascade of errors resulting from that. Okay. So I mentioned that private variables are uninitialized by default at the start of the parallel region. Okay. We can change that behavior if we want to. If we want to initialize them, then we can use the first private clause instead of private. Okay, so this behaves exactly the same as the first private clause. So it creates a new copy of the variables in the list for every thread. But those private copies are initialized with the value that the original variable contained at the start of the parallel region. So essentially makes a copy of the value, not just of the storage in the original variable, but actually of its value as well. However, it's important to note that actually use cases for this are surprisingly uncommon. So if you think you need first private, just take a moment to think twice and think about why you're doing it, because, as I say, it's rarely needed. There are some use cases, but they are fairly uncommon. Again, this works for C++ objects. So in this case, the default copy constructor will be used to create and initialize the new object from the original storage.
Can I just ask quickly on that previous slide, using the first private? So would a use case be if you need to keep track of the state of some variable that is used within the parallel region?
I'm not quite sure what you've got in mind there.
I'm thinking sort of in terms of atmospheric processes that you may need to, again, just running off the top of my head here, you may need to keep the state of, say, the temperature, the pressure, and humidity before you go into the parallel loop, the parallel section.
Yeah, it depends. You know, if you're just going to read those values and not modify them, then it's fine to just keep it as shared and read the original value.
Right.
Okay. If you want the existing value and you're going to modify it, and you want to throw those modifications away at the end of the parallel region, then that's what first private would do.
Right. Okay.
But you can see that that's kind of a slightly odd thing to want to do, right? Because if you're most likely, if you want to modify those values, you want to keep them.
Yes.
And not throw them away and revert to the old value after the parallel region exits.
Okay, thanks.
Yeah. So it is a slightly odd thing. You know, say I want a copy. I want the original value. I'm going to change it. It's going to get different values on different threads, but then I'm going to chuck it away. I just want those. I want to chuck those modifications away at the end of the parallel region. So it's a slightly unusual use case. So if that makes sense. Okay, so here's a seriously contrived example. Okay, so suppose I do a similar thing of adding operating on elements of an array here. But so what I can do is say suppose I have a variable b that has some initial value. Okay. Then if I declare that as first private, every thread gets a copy of B, which will be initialized to the value 23.0. I can then go ahead and say accumulate those values into the private copies, okay, and then store them somewhere. Okay, so maybe store them in the last row of the array or whatever I do. Okay, and then the actual storage of B disappears at the end of the parallel region. So it's possible, but it's really quite contrived, and you actually in practice very seldom need to do it, but that facility is there. Same deal with Fortran. Okay, so far the options we have for variables inside a parallel region are shared, private, or first private. And then there's one more option, and that's to handle reductions. So if we remember, so reduction is one of these operations that produces a single value from associative operations, such as addition, multiplication, max, min, and or, and so on. So in this case, what we would like is each thread to accumulate into a private copy and then reduce all those at the end to give the final result. So in the syntax for this looks kind of similar, but we need to specify the operator as well as the variables. So the syntax looks like reduction, open brackets, then specify the operator, then colon, and then list of variables. So this also works. So actually, I should have mentioned, private, for example, works for arrays. Okay, so that's clear what that means in Fortran. In C or C++, I will get if it really is genuinely an array. Okay, then I will get a copy of the array if I declare it as private. If it's actually a pointer to some dynamically allocated storage, then all I get is a copy of the pointer. Okay. However, for reductions, the situation is slightly different. We can do reductions on arrays, and the meaning of that is that the reduction operation is done separately on each element. Okay, so the result is also, so every thread gets a private copy of the array, but the result is still an array. Okay, so it's not collapsing, it's not forming the sum of the array into a scalar. It's just doing the reduction operation individually on every array element. Again, for Fortran, that's clear because arrays are well, Fortran arrays are Fortran arrays, and in C++, we need a special syntax which is used for array sections to specify the extent of the array here. Okay, so this still works with dynamically allocated storage, which is if we have a pointer to some dynamically allocated storage, this still works, but we need to use this special syntax, this square bracket syntax, to specify the starting element, okay, the first element of the array, and also the number of elements it contains, the number of elements that the private copies will contain. Okay. So this is because for dynamically allocated storage, the compiler has no idea how big that storage is. So we have to have a way of telling the compiler how big those private copies are going to be, because if it's just a pointer to some malloc to memory, the compiler has no idea how big it is. The simple example, again, most use cases is for scalars. And the way this works, so for parallel regions, this looks slightly odd. Again, mostly this gets, this will be mostly using this for parallel loops, in which case the behavior becomes much or seems more natural anyway. So what happens is, okay, so if we declare a variable, so we've got an integer b here, which has some initial value 10. If we declare that as a reduction in the parallel region with the plus operator, then what will happen here is that essentially the value in the original variable is remembered. Okay. Every thread at the start of the parallel region will get a private copy of B. And because the operator is addition, those private copies will be initialized to 0. So the initialized value depends on the operator. So formally what it is the identity element for the operator. Okay, so for addition it's 0, for multiplication it would be 1. If it's a maximum, it would be minus the or the most negative number representable in that type. For example. Okay, so we get these initialized private copies. Then all the accesses to that variable inside the parallel region refer to those private copies. And there's actually no restriction on what you do to them. Okay, so just because you've declared them as declared an addition here doesn't restrict you in what you're allowed to do to those private copies. You can use them as you like and store anything you like in them. But then what happens at the end of the parallel region, all those private copies are then added back into the original variable. So the final value that we get at the end of the parallel region is whatever the original value was plus the sum of all the private copies. So that may seem slightly strange. When we come to use it with parallel loops, then you'll see that that's kind of the natural semantics to mean that you can just use reduction clauses and not change any underlying code. Anyway, we'll see that in the practical exercises. Okay, and exactly the same deal for Fortran as well. No differences except for the allowable operators. Okay, so okay, I haven't explicitly listed those here, but effectively it's everything you'd want. And in C++, you can use max or min do work as operators, even though those things don't exist in the underlying language. They are suitably defined in the same way that you would essentially. They are defined in the same way that you would normally define them using a macro. Okay, there's a classic way of defining of having everybody does to use to define max and min. As a macro in C, you can just use max and min as reduction operators, and it behaves in exactly the same way as the classic macro that anybody would write. Let's say addition, max, and min are by far the vast majority of use cases here. Other operators you see extremely rarely in real code. Okay. Any questions? Okay, so we come to the exercises practical session this afternoon. After you've done the simple hello world example, the first sort of real coding example is just to introduce you to using parallel regions. So it's a very simple piece of code which produces an estimate of the area of the Mandelbrot set. So Mandelbrot set, I'm sure you all know, is this very, very famous fractal. Perhaps surprisingly, for a fractal, it does have a mathematically well-defined area. So we can estimate that by essentially putting a grid of numbers, a grid of complex numbers in the box that surrounds the set. Okay, so just populate that with a two-dimensional grid of values, and then test each of those values to see whether it belongs to the set or not, and then use the ratio of points inside to the total number of points, multiply that by the area of the box, and that gives us an estimate of the area. And very nice parallel problem, because every single point, testing of every single point is independent. So we can just get multiple threads to do subsets of the grid of points, and we've solved the problem in parallel. So it's a nice compact little example to get you started. But that's what we'll get into this afternoon. Okay, so if there's any questions, then please shout out now. Otherwise, we will have a practical session this afternoon. Myself and my colleague Queven will be online to help you out and answer any questions, help you if you have any problems logging on to ARCHER2. It's slightly complicated, can be slightly complicated because of the SSH keys and so on. But we'll do our best to get you up and running and answer any questions and support you with the practical exercises this afternoon. Okay.
Mark, can I just quickly ask what text editors are available to use on Archer?
VI, Vim, Emacs. Probably not much else. Maybe not much else. Let me see what else there is on there.
So they're also command line editors.
You can run Emacs in a window if you want to.
Right.
In the next window. If you provided you have the appropriate X handling on your laptop side, you want to use SSH. If you're coming in with SSH, SSH minus Y, minus capital Y to connect, and that will allow you to export an X Windows
right
back to your laptop.
Okay, thanks.
Otherwise, it's inner command Windows stuff. Let me just check and see if there's anything else available by default. I think the answer is probably not. I think not, but if you have a favorite one, try typing the command and see what happens. Okay, Sahil says, could I explain the reductions? Yeah, I can go over. Is it like a special case of function? Okay. So maybe I should go back to my first set of slides. Okay, so let me go back to my sort of original motivating example for reductions here, which would be a loop like this. Okay, so basically want to form the sum of the elements in an array. Okay, and so the question is, how can we do that in a way that's that exploits the parallelism and is safe from race conditions? Okay, because if we simply try and execute these loop iterations in parallel, and if b is just an ordinary shared variable, then we have this problem where these accesses to B, if these are done in parallel by multiple threads, then we have a race condition. We've got this problem where we have multiple threads all trying to add to the same shared memory location at the same time. So the way we would like to solve this problem is by giving every thread its own private copy of B. Okay. So each thread can compute a partial sum, a sum of the subset of the array elements that it computes, and then have those values added together at the end to form the correct final result. Okay, so that's what the reduction clause is doing. So that will, as you'll see when we come to the examples. So we're using the C code. Okay, so the question is, this is just plain old C code. Okay, so the question is, how would you? But if for a very large n, that might be, we might want to execute this in parallel. Okay, so clearly we need to we'll add some OpenMP directives to do that. But what the reduction clause does is it provides us with, so that lets OpenMP do this process for you of creating private copies, initializing them correctly, and then combining them at the end to form the complete sum. We use any associative. Yes, you can. Okay, so you can use addition, multiplication, maximum, minimum, say logical and, logical or. So all those work. So essentially any operator that's associative. It's also possible in OpenMP to define your own reduction operators as well. Okay, so there's particularly for object-oriented programming, if you have operators on objects which are associative, then you can define your own reduction operators. There's a mechanism for doing that. So the basic ones are essentially the ones you will find in the underlying language, including max and min for C and C++, which aren't in the base language. But then you can also define your own as well. Okay, but addition, max and min, common use cases applied to basic types in the underlying language, and you don't need to define anything yourself. Okay, good. Let's take our lunch break now, and I'll be back with my colleague Quevin at 1:30 support you with the practical sessions this afternoon. See you later.